All right, so we have 42, 44 due today. I can go over that. And then I pushed you forward into chapter 4. So 1, 2, and 9. 1 and 2 will be pretty easy. After I review 42 and 44, we'll do a little chapter 4 stuff. And then after all that, we'll take the quiz. Quiz will go pretty quick for you, I believe. So we'll see. So that's our calendar. A week from today, exam 1. So there we go. Good times. $42 look like this, I hope. Right, Nick?
Yes.
Yeah, good. We don't want to do the wrong problem. Yeah, I know. It's a find the resultant with respect to O, and we have some angled forces. So the way to deal with angled forces is to turn them into their components right away. So the components are here and here, here, and here. But we need to build triangles to find those components. So this is where we kind of move the vertical one over here to make our triangle, but it's really here. And this vertical one over here to make this triangle. So however you want to do that, I typically pull them off to the side or do the calculations off to the side. But this is the Y, this is the X of the 15, this is the Y, and this is the X of the 25. So once you have those components, then you can forget about these forces on an angle. You can just use the components, right? Because the components are exactly the same as the existing force. So let's grind through that. Using the 75 degrees, opposite is the Y. So sine 75 equals opposite Y of the 15 over 15K. So Y of the 15 would be 14,488. Okay, it's going down. You want to be careful with this step, because if you muck any of this step up, then it's just all wrong all the way through. So that's disappointing. Cosine of the 75 is going to equal adjacent, that's the X of the 15 kip force over 15K. So the X of the 15 equals 38823. That one going this way, this one going this way. All right, so that's these two here. And now I'm going to get these two. So I'm just going to get all these components right away. If I was doing it like, I don't know, for somebody else, I might redraw the beam and then put those components in. But I'm just going to roll with this, redraw the beam when I have it all collected at O. All right, so then we were given this rise run thing where the rise is 12 and the run is 5. That's a pretty odd rise run, but I'm going to get this angle first. So if I go for this lower angle down here, that's going to be tangent minus 1, 12, opposite over adjacent 5. So that would be this little lower angle right there. So I'm going to use my triangle on this side. So 12, 5, 67, 38. 0, 1 degrees. So again, that's that lower angle. Can't reach it, but I put a little arc in there. So now I'll use that angle. Opposite is going to be the y. So sine 67.38. I'm going to round that, but I won't use that when I actually calculate. And then that's going to be the y of the 25 over 25k. So just finding those components of those angled forces first. $23,0769. That's down. It's the y component of the 25. And then so the other one, the x, would be cosine 67.80. Again, I'm not. Oh, that was a punch. 38. I'm not using this rounded number. That would be adjacent, which is x, adjacent to that angle, over 25. It's cosine. 9.6154. It's the x of the 25, and it looks like it's pointing this way. So you have to keep those directions straight, because now we're going to move it all. Now that I have essentially a parallel system like we practiced, and then a couple x forces, I can just move that all to O pretty easily, because now the moments are all clean as far as force times distance. So I'm going to redraw point O right here. O. And I'm just going to move all the forces over and their moments. So I'll move the 10K. And its moment, which is what? Yeah, 10 times 8 is 80, and it is clockwise. $80 kip feet, and I'm actually going to write it as negative because I'm going to end up with a few moments here. I want to keep track of them. So the 10's moved. Now I'm going to move the y component of the 15 because the 15 is gone. I'm using these components. So the y component of the 15 is 14,488. And I need its moment. So that's this one times 8 and 6 is 14. So take that 14,888 times 14, 202,8444. And its rotation is that same way. Stop me if I'm losing you or if you're confused. Ask the question. That was this one I moved because the 15's gone, so I moved the y component. I'm going to move the x component because it's got to be over here. So the x component of the 15 is 3.88, and it points to the right. It's only 2 of those 8s and 2, 3. and it's positive. Does that X component create moment about 0.0? Or does it go straight through the point? Yeah, if it goes straight through the point, it does not create moment. So we just move it. So no additional moment for this X, no additional moment for this X. Just move them over. So I'm gonna just move this thing over. X of the 25 is 961. It points the other way. I'll put it out here. But it's going through O, right? So that one's moved over, that one's moved over, that one's moved over. I need to move this one, the Y component of the 25. And I'll just put it down here, stacking them all up at 0.0. And that is 23.0769K, and that's down. We have them all moved. The 10K is over there, the Y component of the 15K, the X component, the X and Y component of the 25. This is what you end up with when you have forces at an angle. You end up with all these X effects, these Y effects, and these moments collected at O. Now we add them up. Any questions on that? Everyone see where I got those numbers? I'm not supposed to ask that. Are there any questions? I'm supposed to say, what are your questions? Implying that you have them. Maybe not. Maybe we're good. All right. So I am going to move down a little and just work with that because that's everything now. My 0.0 and everything that's collected. So then here's O again. 0.0. Add up all the downforce and I get, I don't know, I'll have to do that. The 14, the 23, oops.
Wait, why didn't we times the 23 by? Like we did with the 14.
We did. So when we moved the Y, which is 23.
Yeah.
We multiplied by 14 to get the 202, didn't we? Do we have
Well,
three
that was
mo,
the
1, 2, 3? No, we haven't done that moment yet, have we? Yeah, we gotta do them. We should have 3 moments.
Yeah.
1, 2, 3. And I only have 2. I must have just skipped that step. So it should be 23 times this full distance, 11, 19. Yeah, good catch. Okay, so I gotta clear this. Oops, damn. Lost my numbers. I'm so sad. .0769 and 19. Oh, 19. So it's this Y component times 19. Yeah, it's a big moment too. Same rotation. Yeah, I was just moving right along, wasn't I? 438.461. Yeah, so all of those moments are negative. All right, good catch. Thank you. Now we can add them all up. So I'll add up the Y forces, 23, 10, and the 14. Get 47. Point.
We added up the kids.
These, no,
Oh.
doing the vectors first, just the vectors. But then I will add up the moments. Total down effect is 47.5657, if I didn't muck that up. So you got one?
I got 47.9.
So you just did the 14 plus the 10 plus the 23.
Yeah,
I got what you got. Yeah, I got
Okay.
what you got.
all right, just keep going.
I probably just.
You probably had some rounding, yeah, rounding. All right, let's add up the X's. Those are just two of them, right? 3 going to the right, 9 going to the left. So I will carry all that. 3.
That's with negatives and positives.
You don't, as long as you have your directions. I mean, I do just because that's what you end up doing to get this 5.7271. But like at this stage, all I care about is that I have the correct directions. I know I have 5 going left and 47 going down, right? And I do graphically draw it this way because it's gonna end up to create the resultant. And it'll tell you the quadrant and location of where the resultant is. So that's important. All right, and then we add our moments up. So just summing everything up, this is the kip feet, 80 and 202 and 438. $6.47.
They were all running some direction.
They were, yep,
80 and the 202 and the 438.
yeah, these 3. All rotating. Okay, let me do it again. 438, enter, the 80. Whoa. Oh, I'm not entering twice. Yeah, I screwed it up. 4, 202. 721, 3055. That's why we work in pencil. So at this stage, I actually find out the location of the moment, or the location of the resultant. So here's my beam from here to here, because this is the force I use to get the perpendicular distance. I use that Y force. The X force does not contribute to that moment. That moment is created all by the Y force. And I know that R is like down here somewhere, and so R is going to be out here somewhere. And I can get that from Pythagorean theorem.
Why is on?
Good question. Why is it out there? How do I know
Because
that R is out here somewhere?
Because the horse is down, so it has to.
That's why it's pointing down.
Oh.
But why is it out here and not like over here? Because what? Because of the rotation, that's exactly right. This force, R, has to make that rotation, that effect. So therefore, it's gotta be over here, which creates the same kind of rotation. If R was over here pointing down, it would create the opposite rotation. And we have to make this by setting this over here. So the moment tells you which direction R goes. It has to be over here. To create that rotation.
But it goes at an angle.
Because it's the addition of these two, right? R. This is R right here.
Okay.
So it's this down and this over, it makes R. Parallelograms, how we know.
Oh,
Remember that? So this goes here and this closes it, that's R. the combination of these two. So that's how I know it's down and at an angle.
In previous ones, we've just left it going through
The point?
the point.
Yeah, no, the last couple problems, we started moving the resultant out onto the beam.
Okay.
Yeah, because it's really out somewhere on the beam. I mean, we get the resultant because we have these two magnitudes, we can do pathetic green theorem, we know the magnitude of the resultant. We just don't know where it is. And it's not here because of this moment. If there was no moment for some reason, then it must be right there. Not creating a moment, right? But since there is a leftover moment here, that means R is out there or something. And we have to find out where it is. And if we know these components are the same effect, then this X just drops out of the moment equation, just like it did above, right? These X forces dropped out of the moment equation because they went right through it. So this is the same concept. This X force does not contribute to that moment. It's all this Y. So to get the perpendicular distance or the distance out on the beam, we take the moment and divide by the force of the Y to get a distance in the X. That's this thing, distance in the X. So that's the 721 divided by the Y component 47. It's out there 15.16 feet. I think that's rounded correct. Yeah, 16 feet. That's where R is. So that's a tricky step. Like you got to do that one a few times to kind of get full comprehension of what the hell's going on here. Right.
Just the right of point out.
Yeah, that would say right of 0.0, and we still have to find R, so we gotta do pathetic green theorem to find this thing, because I really don't know what it's equal to yet. So that squared plus that squared equals that. It's amazingly close to the Y because Y is so big and X is so small. I get 47.91 kips. And really, the last thing you would need is like the angle in which it acts on. Because it's some random angle, right? And we get that, again, we get that from our triangle here. So this is the one I would want. I would want the angle to horizontal. That's the most common. So this and this are the same, angle to horizontal, angle to horizontal. So that's going to be the inverse tangent of Y over X.
So if you were to still find that bottom left angle, is it
This one?
or down?
This one?
No, to the, well, maybe it's the one you first pointed. Yeah, that
This one. Yeah, that's the
one.
one.
But the other one, the down opposite.
This one.
That one.
Yeah, you can
Same
do that.
thing.
Absolutely.
Okay.
Opposite would be Y over X. This one, Y over X. Same thing. Yep. $83.18. That's what I get. They're complicated and they're a bit messy. So just use like a lot of paper, spread it out. Yeah,
The moment, which is 17.1
yep,
over. Fourth of Y is 5.73.
no, that's X,
Oh.
Y is 47. Yep. Easy to get them switched, like. You can get them switched doing the trig, you can get them switched just writing them down. Lots of opportunities for error. So somebody always looks over my work when I do any kind of equilibrium type problems, which is what we're heading towards. It's just easy to make a mistake, so. It's good to do it and compare. And then, do it in some form like this that makes sense to somebody else. So when you're talking with somebody on the phone, you can say, hey, what'd you get for the X of the 15 kip force, right? Should be able to find that pretty easy. X of the 15 right here. All right, what'd you get for the Y of the 25? Well, that's here. So keep it that kind of clean and you can compare with somebody else or have a conversation with somebody else fairly easy. What'd you get for the total moment? What'd you get for the total, Y force? What'd you get for the total X force? That kind of thing. So that notation's pretty important. You will not have an angled force on the quiz, so that'll keep it a little bit simple. But we need to practice these, so we can do them. All right, let's do the next one. 44. I hope it looks like that. Oh, good. I want to do the wrong problem. I have 40 kilonewton meter distribution on top, 100 kilonewton meter distribution down below, going to 0 right here. So statics, the first thing we do, yeah. Am I missing a concentration?
50 goes down on the.
That
left,
50
right, left,
goes
so-
down
At the end of 2 meters?
Yeah.
Aha. That's important.
Down.
50 must be kilonewtons.
It starts at the corner.
Is it hanging down?
Yeah.
So it doesn't matter that I drew it this way?
That's all.
No.
Principle of transmissibility, that's what that principle was. Forces can lie anywhere along their line of action. So that's cool. You can draw it down here. What's funny is you can draw it like down here. You can draw it anywhere you want along this line of action. So that's cool. Keep that in mind, though. That's important. Like you can move forces anywhere along their line of action. All right. Statics says whenever you see problems like this, the first thing you do is concentrate the distributions. Get rid of the distributions. So how do we do that? Like if it was a quiz question, how do we concentrate distributions? You would answer.
Wait, so
We want to concentrate that. We want to concentrate that. Turn it into a single force.
area,
What about the area?
um,
Find the area and that's the what? That's the magnitude of the force.
Put that.
And you put that not in the middle,
The center, the geometric center.
geometric center of the
Shape.
shape. Excellent. I'll put that on the next quiz. So rectangle is easy, right? Because we know where the center is. It's right there. Halfway, it's at 2 meters, right? And also it's an easy area to calculate. Area of a rectangle is base times height, 2 times what? 2 times 40. 80 kilonewtons. And now that distribution is gone. 1 meter and 1 meter. We do the same thing with a triangle. Anyone know the area of a triangle? Yes, it is 1/2 base times height. So it is 1/2 100 kilonewtons per meter times the height of 4 meters. Looks like that's 50 times 4, which is 200. Is that right?
Yeah.
And where does it go? That's true. I remember that. But if I don't remember it, I go to the front of the book and I say, oh, look, there's a triangle and check it out. It's base divided by 3 this way, and it's base divided by 3 this way. So it really doesn't matter which position your right triangle is in. It's the base divided by 3. So I know it's here, so that means, oh, it's this divided by 3. So this distance here is 4/3 meters from there to there. You can calculate that, 1 point, whatever. I'll just write it 4/3. It's 1.93444. Is that right? 4 enter 3 divide. No, it's 1.333. Good question. No, don't answer that. Kevin's gonna think about this for a second. This is the concentration, right? So this is the concentration of this triangle. So when we did this, that's the area of the triangle. It's equal to that, 200. So this equals 200 kilonewtons. So the area of the distribution is how we get that concentration force. That answer that question? Got it, Kevin?
Yeah.
All right. Rock and roll. We're now ready to work the problem. After we have concentrated all the distributions, this triangle's gone, this rectangle's gone, 80 kilonewtons is in, 200 kilonewtons is in. Now, what's the problem want to know? Probably the resultant. Did it say respect A? Or did it say, is this the one that said, and where it intersects the grade?
Yeah.
Yeah, so this is kind of a trick problem. So they want to know, so here's this structure. Oh, I should do it so it's recorded. All right. I'm just going to give you some concepts here, and you can talk me through this. Where do you think we want to collect everything?
Okay.
Sure, down at A?
Yeah.
Yeah, that makes sense. So I'm just gonna do it, I'm gonna not do it mathematically, I'm just gonna give you kind of a big concept, but if we're gonna collect it all down here at A, then we move everything down, right? 200 comes down. Right? I don't have to calculate anything to know this step. What else comes down?
80 kilo.
The 80 kilonewtons comes down, thank you. What else? The 50 comes down. Anything else? No, that's it, right? There's only 3 forces up there, and it all comes down. Agreed? We're not calculating anything yet, but we're just moved everything down there, but we'd also have to bring the moment down, right? So, not gonna calculate it, I'm just gonna put in the moment rotations. So what about the 200? Which way is it rotating about A? Clockwise. Agreed. What about the 50? Yeah, so I kind of move it down here in my mind and then I spin it around A, and it's definitely counterclockwise. What about the 80? Yeah, again, I move it down here and then I spin it and it's definitely counterclockwise. So there's the 3 moments that come down. I don't know their magnitude, but I could calculate it. That's force times distance, right? Yeah. All right, now I'm going to conceptually think about the resultant. Where's it at? Again, I don't know its magnitude, but where is it?
somewhere down.
Yeah, if I do my little parallelogram law, this is about this, it's like really kind of 45-ish. R. Agreed? That's from the parallelogram law, R is like that. All right,
Why is it going to X?
oh, that's a great point. It's not, it's going this way, correct? Because the X is going over here. So R is down here somewhere. Good, Juan. Everyone see why it's over there? Yeah. It's a good catch, because we're doing this kind of conceptually. So then I have to figure out like, well, if these two moments are big and this one's small, which I think it is, this is a small moment and these are going to be bigger. R is going to move up into here somewhere, R. Just conceptually. Once we move it, it'll be up on the structure somewhere, right? Do you agree with that? Yeah. So the problem says, find out where R is on the system and where it would intersect the grade. So R is up on the structure somewhere, but we know R has a line of action, right? Boom, right there is where R intersects the grade, back down to the ground. Wow, that's an interesting concept. But that's what they're talking about. This is the problem that says that, right? Yeah, okay. So what's fun is, well, what's different is you do this on telephone pole problem. I think I mentioned that the other day, that we want the resultant to be down through the concrete. So the resultants on telephone poles, we want them pretty damn vertical. They can move a little, but they need to intersect the concrete down below. That indicates stability. Okay. The other thing we do this all the time on is gravity dams. Right? So that's a gravity dam. That's water. This is gravity dam or earth dam is where you just take earth and hold water back, which is a primary way we do dams. Drive along the Columbia, if you're driving on Marine Drive, that is a gravity dike holding water back.
What, the part on the road that you're on? Where
Yeah, keeps the water from going into the Portland airport. And the rest of the area, it's a giant area that we're holding the.
They add so that it's taller than the
Oh,
road.
well, we add, so it's taller than the maximum flood point. So when we have this crazy meltdown in the spring and all this rain, everything's flooding and the river's rising, it comes up that dike quite a ways. Right? So if we build it right, that holds. So here's the deal, water pressure creates this kind of a load diagram, right? Bunch of pressure at the bottom where the water's deep, no pressure at the top where there is no water, right? So then that creates this. Water pressure, we just did that, right? We know now that, oh, water's creating this concentrated load right here. Well, this has what to it? Weight. It's heavy. We like it to be really heavy. It's a big concentration, right? So we could concentrate it, ends up to be like right in here somewhere. That's the weight of the dam. Does that make sense? Acting down. Guess what? I can move the water pressure anywhere along its line of action. So I move it over here. Boom. We know that's fair, right? And I move this one down, boom. Now I have here and here, where's the resultant? R. Right, that's exactly what we just did on this problem. Here's the deal, if R intersects the base of the gravity dam, it is stable. And it will remain stable. If R is outside of the base, in other words, if this was so high and this was so skinny that R went out here, that design is not going to hold up. Water pressure is just going to push that gravity dam right over. So we do this whole like, where's R and where does it intersect the base? We do it quite a bit. We do it in telephone poles, we do it in gravity dams. never done it in something like this, but this is kind of a telephone pole, so I get it. Right? Alright. That's a big sidebar, but I like damn problems. I like to say damn problems. They're good damn problems, so anyway. Alright, so how do we do this? How do we solve it? We have a lot of it done. We need the moments. So let's get the moment for the 280 and the 50. I'll let you do that and I'll do it at the same time. Maybe you've already done it. Homework problem. Maybe not. Either way. The 50 is 50 times 2. So I'll just pick one of these. So this is the moment of 50. Eighty.
Can I just check something real quick?
Mhm.
You have kilonewtons written down several times. I only see newtons on here,
Oh,
or newton meters.
that's probably me. I just assume kilonewtons. Is it meters? Is it newton?
Newton meters, or newtons, yeah.
It's just newtons.
It's just newtons.
Yeah, I just dropped my K. Well, I'll drop my K. But I have it in ink several times, so let's scratch it out.
Let's make sure that the moments are.
Yeah, they should be. Did I get my moment right? 86.6. Right? So I got the resultant. How'd I get that?
The case reference piece.
Yep, Pythagorean theorem of the y and the 200. So it's like 130 and 200. Pythagorean theorem. Gives me 238.54. And then I found the location of R by taking that moment and dividing by whatever's creating the moment. So if I look at these two components, the y component does not create moment, it drops out. All of the moments created by the x component is 200. So I take the moment, divide by 200 to get a y distance. That's trick. Huh? Yeah. So that, look for M 200 right here. 266, are you saying, how'd I get it?
Yes.
Up here. So it's 200 times the distance. And the distance of a triangle is 1/3 of that distance, or 1/3 of this distance, whichever one you need. We needed 1/3 of 4, so that's 4/3 or 1.333. So it's really pretty close to the base. It's only a half a meter, a little less than half a meter from that bottom point A. So my drawing's out of scale. This one here, right? Because I know this dy is only 0.43 meters up. So if I can get the angle that R acts on, then I can get this x distance. That would be where it intersects the grade. So I can get this angle just by doing the arctangent of x over y. X is 200, y is 130. So arctangent x . 56,976. Then with that angle and this distance, I can get this distance. I probably use the tangent, which is opposite over adjacent. Because I know adjacent is 0.43. I know the angle, and I want that.
The arctan of what?
For this,
Yeah.
opposite over adjacent. So arctangent of this was 200. So I used vectors for that, right? So this is 200. That's this thing. And then the y is 130.
Okay.
So you pop back and forth between using distances and using angles. So we used vectors to get that angle. Then we got that angle. Now I'm going to use distances to get that distance. So the 0.43 meters. So you've got to flip back and forth. So tangent of the 56,976 equals opposite x over adjacent 0.43 meters. This x distance equals that times that. .66 meters. Tricky, man. That's a long process to get from the given distributions to all the concentrations, to putting them all at one location, to finding the resultant, and then shooting the resultant down to see where it intersects the grade. It's a big, long process. Yeah, No, it is. Like, finding the resultant is complicated enough, but then they're asking to shoot it down through. But it's a very legitimate question, like it gives you stability or not. So, 0.66 meters is where that resultant intersects the grade. So this thing, it's gotta have some kind of support underground, and that would tell me that we need to be at least 1 meter each side of the pole. So that's a big area of concrete, but it's carrying a huge load, like these are big loads. Big twisting moments, right? These moments are trying to tip this thing over. So some substantial supports needed. Boom. Awesome homework right there. What's the most confusing part on this thing? Hmm?
So, like,
What about, let's start at the beginning. So the distributions, are you okay with that? Concentrating those things? Yeah. Okay. Good. And then what about collecting everything at one spot? That's this phase right here.
I think that's pretty good.
Getting that down pretty good.
I think it's part of finding like almost what angle, actually that's kind of simple, but the dy or there's a new formula.
It's like, oh, now we have R, right? We can get R here, but we have to move R back up onto the system. I think you guys are getting that.
I think at a certain point, you've just done so many things and so many things that when you're doing the math, it's hard to conceptualize
Yeah.
where you got everything
Yeah.
from, because it was so.
Dude,
R.
wait until, well, you've had strength of materials, but. So strength of materials, this is all lead up to a strength of materials problem that is just as long. Okay, so we'll get like halfway through a problem and then I'll go like, what are we doing? And you'll go like, we don't even know what we're doing. Like, where are we at in the flow of this problem, right? So it's really hard to keep track of where you're at in the flow of the problem. Use a lot of paper and try to keep track of it. Like,
Being organized.
it's really big, and it wouldn't hurt to like label what you're doing, right? So we're collecting everything at O here. So I could actually write that, collecting at O, and then that could be just a block of the paper, right? Then we're like determining the resultant. That could be, down here somewhere. And then it could go to the next part, which is shooting the resultant somewhere. This one, it's shooting it through the base, but if you have horizontal problems, you can shoot at other places, right? So that concept of, oh, vectors have a line of action and it can intersect anywhere. They could have asked us, does it intersect the top? Right? And we could calculate that. You just get an angle and do some trig and go, oh yeah, it intersects the top, or no, it doesn't.
Well, doesn't it intersect at a point with the structure?
Yeah,
So there is a point where it intersects.
The
on
top?
all of those.
yeah, I don't know that it does, because this, graphically, the resultant is like right here. Right? It's really down at the bottom. And it's pretty steep. It's at what angle? 56. So it's down here at 56. I bet it doesn't intersect the top. Follow me? Yeah. So my graphic down here is just way off proportionally.
You only work if you draw and like doing accurate angles.
Yeah. Yep. We could calculate it to figure it out if it does or not, but my guess is it doesn't even come close to the top. Yeah, and on a gravity dam, like, if this is just too narrow, then R leaves the base. It's not through the, if this dam was really tall and then this skinny, R ends, and then the water's up here, R ends up to be up here somewhere, right? And then it intersects out there and it's not stable. So there's definitely other characteristics to make it stable, but this is a big one, so. All right, well, let's turn those in and take a little break before I do just the beginning of chapter 4. I won't get too complicated with it. Good. Short break.